All right, so now we're in chapter 4 on analyzing change. We're looking at applications of derivatives. So in section 4.1 here, we're looking at linearization and estimates. So what are estimates of change? Well, we've seen in previous chapters that on a small interval around a point on a differentiable function, such as our blue line here, the function and the tangent line to that function at a point appear to be then same and known as linearity. So if we blow that area up, make it really big, we could even blow that up again here and make it big, those will start getting to be about the same. They're going to look like the same linearity. Okay, and so then the rate of change of a function may be used then to approximate the change in a function over a small input interval. So again, changing it to a small input interval, looking at it, we can say that rate of change is going to approximate the change in a function. So we can write that. So we have some small change h, and on our graph here we have h is right here, and it's just from here to here. So remember we did the algebraically adding a point, then a point plus h, and that's kind of what we're doing here. The input x of a differentiable function f, the rate of change of f, times the small change h in the input can be used to approximate the change in the output of f. That is, for some constant input c, the derivative of f with respect to c times h is approximately the f of c plus h minus f of c. So here's our, f of c and then f of c plus h. So that gives us that difference here. If we look over here, it kind of be that difference. And then we can take this f of c prime times h, which is this, that would give us approximation. Now notice this is a difference. There's going to be a difference. So depending on how small you go, this will get smaller and smaller and smaller. But if you make that really big of h, then that's going to be a pretty big difference depending on how the curve is shaped and the curvature of the function at that point. So a change in the function output f of x from the point of tangency, our cf of c, so we're going to have some point of tangency, to a nearby point c plus h times f of c plus h. So that's going to be out here. It's going to be estimated by the change in the output of the tangent line over that same input interval. Okay, so the change is computed as the slope of the tangent line times the length of that interval. So we're going to do the slope times that length, and we're going to say, well, that's going to be less than or equal to that derivative at c times h. So we're going to kind of start interchanging. And so if we look at an example based kind of on what we're looking at here, so if we have some function g, and the output of g of 10 is equal to 5, and the derivative of at 10 is equal to 2, then the change from g of 10.7 to 10, or if we subtract those off, we have our point here, we subtract those off, that's going to be estimated as g prime of 10 times h. So we're going to estimate it as this whole thing times h. So how do we get that? Well, our g prime of 10 we said was 2, so we take 2 times our h. Well, our h is basically going from 0.7 higher than that, so it's just going to be times 0.7, and so that's going to be 1.4. Okay, so that's going to be kind of what it is. Now, what was that actual change here? We'd have to actually calculate it and figure it out. But we're saying with f prime to c times that h, that's what we're going to assume is going to be approximately what that difference there is. All right. Now, from that, it follows that f prime of c times h is about equal to that difference. Okay. Well, can we do anything with that? Well, what we can do is we can solve for this value here, which is what one of the things we're going to need. So we add f of c to both sides, and so we get this formula here is going to be um, basically approximating the change of that function by adding the approximate change to our f of c. So what we have then is approximating the result of change. So we have our small change from, our c over here to c plus h at this point here. And so that distance is h. And so f of c plus h, well, that's going to be up here. And it's going to be about equal to this plus this derivative up to here. So we're going to take the derivative up to here times h, and that's going to approximate the f of c plus h, which is that distance here. Okay, and we can see all that based on the side over here. They've kind of put it on the edge, but we're looking, from here to here. That's what we're looking for. We're approximating it by this here distance and this, and so that gives us an equation we can use to solve f of c plus h. And we have to know f of c, we have to know f prime of c, and we have to know h. So if we're given that, well, g of 10 we know is 5, the derivative is 2, and the output is going to be estimated as, and well, what's that? Well, it's zero point 0.7 higher than that, so it's going to be our 5 plus 2 times zero point 0.7. That gives us 6.4 for g of 10.7. And again, every function is going to be different depending on what your function is, what the, at what point we're looking at, and what the derivative is at that point as well, and then what interval we're looking at for that h value. Okay. Now what we can do is we can do a linearization. So that tangent line may be used for short-term extrapolation. So, maybe we want to go out to a certain point. So it'll work in cases when it makes sense to consider the future behavior is going to kind of follow the rate of change rather than the behavior of the function maybe. So maybe we know that, the function is going to look like that, but the rate of behavior actually might continue on like this. And so for just a short term, a little bitty bit. And so then we can do this linearization model to approximate the function. And so what's going to happen is we're going to do FL of x. So that's the linearization of f with respect to x. And we're going to take our f of c plus our f prime of c times, now instead of h, we're going to say it's x minus c. So then we can plug our c here. So if it's a 10 and a 10 and a 10, then we can check what it is at what x point in the over beyond that. And so, we might choose some x out here. And so maybe that's a 10.7. Well, then it's going to be 10.7 minus 10. So it's a 0.7. We found those derivatives. So it kind of looks like this, except instead of just saying, well, that's 0.7, what we're doing is we're saying, okay, well, when we do that linearization, we're doing 10.7 minus 10, and that's our 0.7. So this is kind of leading up to that thing. And what we're going to do now is we're going to be able to calculate that for any value here. And we just plug in, the 10.7 minus whatever our f of c is. And then, that's going to be given us that whole thing. So we're assuming that the linear behavior is going to continue on like that. And so that's kind of the big key assumption. Now, if we look at this for this function here, for a function g with input x, our output g of 10 is equal to 5, the derivative g prime of 10 is equal to 2, and the linearization of g with respect to 10. So now we're having to assume we're linearizing it with respect to 10. So we're putting our c here is going to be this. And then we can plug in any value for x to kind of figure out where it is on that curve, and then we can do that calculation. All right, so let's stop there and we'll come back with some examples.